Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, how does that robot move like an animal? And how does that thing work? Hello everyone, welcome to Robot Talk. I'm your host, Claire Asher, and this week I'm learning more about bio-inspired robots with a guest whose incredible climbing, flying, and tree planting robots have taken inspiration from some of the coolest animals on Earth. But first, I'd like to invite you to join the Robot Talk community on Patreon, where I'll be sharing behind-the-scenes updates, and you can chat with me and other Robot Talk listeners. You can also sign up to support the podcast for just £5 a month. And if you do, not only will you get a warm, fuzzy feeling for helping me to keep producing and expanding the podcast, but you'll also get access to exclusive bonus episodes and lots of other cool perks. Check out patreon.com/Claire Asher to find out more. So, with all that said, it's time for me to introduce this week's guest. I recently had a fascinating chat with Robert Siddall from the University of Surrey about novel robot designs inspired by the way real animals move. This week, I'm speaking to Robert Siddall, a lecturer in robotics at the University of Surrey, whose work focuses on novel, bio-inspired robot designs to solve important environmental problems. Hi Rob, I'm excited to have you on Robot Talk.
Hi Claire.
So your research centres around robot movement, particularly flight. So to get us started, can you talk a little bit about the kind of current state of the art in robotic locomotion and how that compares to the capabilities of animals?
Sure, yeah. So robots have gotten very good at moving, certainly in the time I've been working on them. I like to sort of give people kind of like the top trumps kind of numbers on locomotion. So the motors we use in the robots today are something like 20 times more powerful, pound for pound, than animal muscle.
Okay.
Even the very best animal muscle. So, we're talking like 10 times better than the flight muscles of a hummingbird. Our materials are stronger. Carbon fiber, again, 10 times stronger than bone, sinew. And even our batteries, which we always complain about as roboticists, are pretty good. I like to give people a comparison. If I took all the food that I ate in a day and I got a battery that held about as much energy, we're talking about a 12-kilo battery, so about the size of a car battery.
Yeah, okay.
And that's actually a pretty fair swap. If you swapped out my, digestive system, all my fat reserves, for that battery, it's a pretty fair swap. I weigh about 100 kilos, so 10% of my body mass. So we're actually doing pretty well in just sort of those kind of raw numbers. But when you look at what animals can do, robots suck.
Yeah.
So, the sort of big question for scientists is why is that? And there are lots and lots and lots of reasons. But I think the thing that really separates animals from machines right now is robustness. I don't know if anyone's ever met a three-legged dog.
I've seen some videos.
Yeah, they walk pretty well. I've even seen a video of a two-legged dog.
Yeah.
But if you were to cut the leg off of one of these robot dogs you see around these days, it would not do a great job. Birds frequently fly with, a bunch of their feathers pulled out. A bat can fly with a hole in its wing. Almost any animal you find swims pretty well. I've seen a sloth swim. Most animals, you can plop them in the water and they'll swim fine. That's also not true of any robot.
So the examples you've just given, what jumps out to me is that the reason that animals can do those things is because they are intelligent in a way. They can they have this adaptability and this ability to apply knowledge they already have to new scenarios. Do you think that is a big part of why robots aren't as good, or is it partly the hardware as well?
I would say it's both. Yeah. So I do a lot of flight. And if you were to take the very best bird, it gets a lift to drag ratio of about 20-1. So it can fly 20 meters forward for every 1 meter it descends.
Okay.
And that's about the same number as you can get for the very best UAVs.
Mm.
But the difference is that UAV can get that in one flight condition at one flight speed. Whereas the albatross can probably do it at a variety of speeds and wind, and that's a mixture of intelligence and hardware. Birds use a lot less energy when they fly, and that's because they're following the wind, and they've got really great sensing for the air, and they're sort of choosing when to fly and where to fly. But they also they can bend their wings, they can morph their wings, and the hardware. If I look at my own foot right now, it's not like a robot's foot. Like, it has a lot of movement, a lot of degrees of freedom, and that's the result of for humans, 50 million years of evolution.
Yeah.
Which is the number I like to tell people. If I were to try and figure out a rough idea for the total number of animal lives that have been lived on the planet, so all the vertebrates, all the animals with spines, the number I get for the total lives lived for every animal that lived and died since spines evolved is something like 1 million times more animal lives than there have been seconds since the Big Bang.
Wow. Yeah.
So the design effort that evolution has done is something we couldn't replicate, even if we tried.
Yeah, exactly. But I guess we can learn from evolution and what the solutions it's come up with and kind of take a bit of a shortcut, hopefully.
Oh, yeah, it's free information. Yeah.
Yeah. So the reason that I originally came across your research is through an annual competition you run called the Natural Robotics Contest, where you ask members of the public to submit their ideas for bio-inspired robots and then turn the winning entry into a real robot, which is just really cool. What was your motivation for setting up this competition?
So the competition actually came out of a little sort of project I did with a journalist. As part of the Humboldt Foundation arranged a sort of like a annual thing where scientists and journalists sit down and come up with ideas, basically.
That sounds fun.
Yeah, it's good. But the reason I sort of proposed the idea was my mom's a school teacher, so I spent a lot of time talking to young kids, and you show them their work, and they immediately start pitching at you, and they sort of say, "Well, can you make your robot do this? Can you make your robot do that?"
Yeah.
And I have fun playing with these ideas. I always thought it'd be nice to sort of turn some of those ideas into reality.
Yeah.
So that's kind of the idea. I'll take all my 3D printers and all my parts and components and let anyone out there in the world throw ideas at me and see if we can build something cool.
Yeah. How challenging is it to take one of these, winning entries and actually make the real robot? Because I'm assuming it's not straightforward.
Yeah, so every year I get the entries and I look through them all, and I get a feel for why I might want to win. I don't control who wins. I basically, there's 5 academics and we all get the same list of entries and we all score them independently, and then we just total them up and see who kept the highest score. And this year there wasn't even a tie, so we didn't have to break a tie. And so it's a little nerve wracking when they go, "I'm gonna have to build something really crazy." But the ideas are pretty good, to be honest. They're pretty thoughtful.
So, the winning entry in 2023 was a seed planting robot inspired by pangolins, which, for listeners who aren't familiar, are these amazing little scaled mammals that live in Asia and Africa. So can you tell us a bit about this robot?
So pangolins, they're the most trafficked animal. Their scales are very valuable. So we based our robot off of a ground pangolin, which you find in South Africa. They're the biggest pangolin, I believe. But I like them because they have this very peculiar gait where they walk on their 2 hind feet, almost like a theropod dinosaur. So, and they're fabulous burrowers. And Dorothy, the girl who proposed the idea, wanted them to plant seeds. And she liked the way that pangolins kind of curl into a ball. And so we went away and we kind of sketched out a variety of ideas. And actually this year was harder than most years. We spent a lot of time trying to make the rolling into a ball thing work, and that didn't quite work. So we ended up having to use the tail more as a counterweight.
Right.
But lots of prototyping, lots of like all kind of robotics. You build it, you test it, you build it again. This year we had to build it again a few times before it worked.
And so it plants seeds?
Yeah, so it plants seed bombs, so like basically little balls of clay filled with, in this case, elm tree seeds.
Okay.
And we have a little conveyor belt inside. We have some claws at the front for digging. So pangolins are great diggers. They like to dig up ants' nests. Their favorite thing to eat is ants and termites. So they're pretty great at digging. So we gave it sort of pangolin-style digging claws. It runs around like a Segway on two wheels, and it has claws at the front. It can dig a hole, and then it can run over, and it can drop seed into the hole. We made the seeds initially come out the mouth, but there are a few mechanical reasons why that didn't work, and so now it poops the seeds, which is a little funny. But.
Amazing. And yeah, I mean, either this one or any of the other entries, have they led to anything kind of that you are then developing further for research or actual applications?
Yeah, I mean, so the seed planting pangolin ties in nicely with some other stuff I've been doing. So you had a few kind of like ground robots running around our campus, doing things like taking inventories of plants with computer vision, taking climate measurements. So it's going to sort of tie in with that whole area of research. And the thing I would like to see robots do eventually is do a little bit of like sort of gentle ecosystem engineering. I think that there's a place in the world for robots that can do things that basically can't happen in our system. So, a good example is England used to be full of wild pigs. And wild pigs are great ecosystem engineers. They dig up funguses, other things. They turn the soil over. And they can really, really do a lot of work. But of course, these days we are not happy with a wild boar running free in a London park. So that role is lost to us. There's a lot of things like that, and large animals, if they're not already extinct, since the Ice Age in the UK, they can't be tolerated in the sort of same space as humans. So there is a world where robots can kind of fill that niche and kind of make the ecosystem better by filling sort of like roles that are lost.
Yeah, absolutely. I guess I mentioned in the intro that you're focused on kind of solving environmental problems, and we haven't quite touched on that yet. So yeah, that's interesting. Do you think people will be more tolerant of robots than they are of wild boar?
Yeah, I think you have to be very careful about how you do this, because the best solution would be just to have real animals do this stuff, right? The best solution is always to let nature do its thing. So you have to make sure you're finding a role where you're not, I don't want to push nature out by saying, "Oh, we don't need you anymore because we've got a robot." But there are things that are just not possible now that still need to happen. And you see it all over the place.
Yeah, I've seen quite a few people mention the idea of replacing declining pollinators with robot bees, and I'm not totally sure how I feel about that one.
Yeah, it's hard to make a robot work harder than a bee.
Exactly. Yeah.
Or better. Yeah. And that's an easy one where I would say, like, people can get stung. That's not that big a deal for most people. Yeah. The bees make the world better for no cost. I picked the wild boar example because that's one that people really can't tolerate. Although, to be honest, a lot of the roles that are lost to us are predator roles, like things like I would love to see wolves back in England.
Yeah, I don't really want robot wolves though.
Yeah, I think it would be a very long time. I think we'll see people on Mars before we see functional robot wolves.
Yeah. So you've also worked on several robots that are inspired by reptiles, including a gliding robot design based around the movement of geckos. So what aspects of reptilian biology have you found most inspiring when you've been designing robots?
Reptiles are fun because they're very different to mammals. They have a lot less kind of like muscle mass. They use less energy during a day, so they're a bit more judicious with their movements. That's not to say that they are like, there's a sort of stereotype of a lazy reptile sitting on a rock sunbasking. Like, reptiles move fast, they are agile, but they're kind of working with less than other similar mammals. So I was looking at geckos, which are about 10 centimeters nose to tail, and they run through the rainforest at sort of breakneck speed looking for bugs. And despite not really being adapted for flying, they are pretty great in the air. So they use their tail kind of like a rudder. They can kind of steer through the air from tree to tree, and they can flip themselves over like a cat. so they can swing their tail around and kind of flip their whole body over if they fall the wrong way. And what I was looking at was how they land. Okay. And most animals that are gliding from tree to tree in a rainforest, they will kind of pitch up and they'll use the air brake. And geckos just kind of hit the tree full in the head. And that was a sort of very interesting behavior, very sort of challenging landing to pull off. Yeah. So we spent a long time trying to figure out how they did that. So we had a lot of video footage that people were working with that collected in the Singapore rainforest. And I built a robot model of geckos, and I spent, the better part of a year flinging these tiny robots around a room, throwing them at the wall, throwing them through the air, trying to figure out. We try to reverse engineer nature. So we have an idea of what might happen, and then we do it with a robot. And by copying the behavior of the robot, we can actually learn more about the behavior in the animal.
Yeah. So when you're doing these things, do you have like an application in mind, or are you kind of does the application come later, and this kind of more about the fundamental challenges in robotics?
That's sort of why I've liked the kind of like biology aspect of it, because when you do engineering research, people always ask you like, what's this worth? What can I sell this for? And people are a lot happier to sort of just say like, oh, this has intrinsic value when you're looking at animals to try to figure out how animals do things. Yeah, I think there is value. It's, we said before, like animals are much better at movement than we are, but working with biologists gives space for some more curiosity research than maybe engineering departments normally like. Mm-hmm.
Yeah, definitely. So what became of your gliding gecko robot?
It's hanging on the wall in my lab. Okay. So yeah, I think it's led to a few more kind of lizard robots, and we're gradually getting them better at flying. And the hope is to try and use them as a way of moving through the air. So I think if you're in practice, you want to build a small robot, at some point that robot's going to fall off something high. For a small robot, a one-story building is a huge drop. And so if we can make robots that are comfortable in the air, we can make robots that will, be able to move for longer and be able to work better. So that's kind of the long-term goal, is just to make robots better at moving. Yeah. And we're working on that.
Awesome. So another project of yours that caught my eye was a flying and diving robot based around seabirds called gannets. So can you tell me a bit more about this robot?
Yeah, that was my PhD thesis. Okay. So I was the first student to join my research group, and that was the first thing we tried to tackle. Was try and make a robot that could dive into the water and come back out and fly away.
That's a pretty ambitious challenge to take on.
Yeah. No, it was very tricky, and we're honestly probably still not there. So it was a research group that is still ongoing, and there are lots of people doing this in other universities now from the same group. So we're still working on it. But the core idea is to be able to sort of sample the water or get water data. Where you have the access to the water, so you can get beneath the surface, you can look around, grab samples from below the surface of the water, but then you can still have the flexibility of flight. So you can, start flying from a few miles away. You can access lakes that are off limits. We all want our water to be sampled very heavily, but it's very labor intensive. Yeah. Right now, if you go to a mountain lake, you want to know that it's safe to swim in. But that requires the government to employ someone with a kayak and some test tubes to go there all the time. So not to mention places that we just don't have any information about. So places that are hard to get to because of their remoteness. So the idea of sampling the water with aircraft is I think is really, really valuable. We made a small kind of like robot that weighed about as much as an iPhone, a bit bigger, about a 1 meter wingspan. It could fold its wings, it could dive into the water. It had some special gearbox so it could move through the water as well as it could move through the air, so using the same propeller. And we took off. The taking off is the hardest part. So to be honest, it's not that hard to crash a plane into water. It's a little bit hard to make it survive, but steering straight down with the plane is not the challenge. The challenge is getting back into the air after you've gone under the water. And we tried exploding sodium into the water to sort of blast us out. Okay. Sodium gives up hydrogen, which you can ignite. We tried we tried compressed gas. So we took off like a flying squid. People probably haven't heard of those, but there are some squid use their jet propulsion to launch into the air. We kind of copied that and used some compressed gas to sort of launch the robot into the air.
Okay.
So there's lots of different things. And it's still an ongoing area of research. So I've just been speaking to someone who is working on a next version of this robot. He's picked up my old PhD thesis and trying to fix the problems that I left behind.
It's interesting because, of course, when you read the description of this robot, you think, firstly, I was kind of expecting it to be flapping wing, just because that's what seabirds do, and then none of the takeoff mechanisms you just mentioned are the one I imagine when I think of birds taking off from water, which is the duck approach of just kind of tread water until you're not treading water anymore. I guess those are the hardest possible things to do with a robot.
They're pretty. Things in the water need to be slow, heavy, and stiff, and things in the air need to be very light and very large. So there's some really diametrically opposed stuff going on. The flapping is an option. There's someone working on that, but I won't spoil the research by talking about it here.
It seems like there's not that much flapping wing flight going on in the robotics world. I've come across a little bit, but it seems to be quite rare.
Yeah, there are a few things you need to do to get flapping right that make it very hard.
Yeah.
So you need to really change your stroke quite dynamically. So not just how much you're flapping, but the actual angle of your wing. And getting that right for engineers requires a lot of computation. Getting that right for animals, it's really an intuition thing.
Yeah.
So there are things like central pattern generators that kind of give animals an intrinsic kind of a mode of flapping that they can kind of tweak as they learn. Which we're doing with robots is harder. You have to kind of do a lot of math, and then you can't do that math for every flight condition. So I think that's one area where I think learning could play a big role. But the hard part is you have to get really good flow sensing on that wing. So what we have right now are typically a flapping wing vehicle is it's a big sheet of nylon that's going up and down, or a big sheet of plastic. I have a PhD student called Owen who is actually looking at exactly this problem. So he is scraping the internet for nest cam videos, and we're actually trying to figure out exactly how birds are learning to fly, what they're doing. And at the same time, we've even built some artificial feathers. So that's another thing that birds have that we don't. Is our feathers are very good. Yeah, but again, I said before, technology is pretty good. The feathers are very impressive, but from a material science point of view, they're made of fingernail. Yeah, they're not made of stainless steel. They're not made of carbon fiber. So it should be possible to do it eventually. Yeah. But it's an area of research that needs a lot more work.
Yeah, it sounds absolutely fascinating. So if you could create a robot that mimics any animal, what animal would you like to make in robot form?
Pterodactyl. Well, I mean, pterodactyls that's not one animal, that's a whole range of them. I would like to try and create a robot that copied an Asdarchid pterosaur. So those are the really, really big ones, like Quetzalcoatlus or Hatzegopteryx. Because I think that there are some tricks that have been lost to time that those animals could employ. So, we're talking about animals that could fly with a wingspan like a Cessna airplane. Yeah. And birds can't get that big. There are some physiological barriers to the birds getting that big. And so, if you gave me anything, I would ask for a giant pterosaur robot.
That would be really cool. It's just fascinating research. I will continue to watch what you get up to with a great deal of interest. Rob, it's been really fun chatting to you today. I've been talking to Robert Siddall from the University of Surrey. Thanks, Rob.
Thanks, Claire.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And make sure you check out @RobotTalkPod on social media to see a photo of the seed-planting pangolin robot that Rob and I talked about. Next week, I'm talking to Anuradha Ranasinghe from Liverpool Hope University about giving robots the sense of touch. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.